Yo, what's up guys? Baby Bear 4812 coming at you one more time. Problem 199, binary tree right side view today, as popularized by Facebook and Amazon predominantly. It's an oldie, it's a goodie, and if you have any other recommendations or requests for follow-up questions, my contact is down in the description below, so feel free to drop me a line and I'll get on it. Now, in this problem, we're given a binary tree, and we need to imagine ourselves standing on the right side of it and return the values of the nodes we see ordered from top to bottom. So imagine taking a tree that looked like this, and I almost imagine this like having a bunch of cue balls from a billiard table and kind of structured like this, and you can kind of turn them to the side one way, and what would you see from top to bottom? That's what we got to print out. In this case, we would have to print out 1, 3, and 4. Notice that we will be printing out the values of these nodes, not the actual nodes, or rather references to the objects in memory. So side point, but something to keep in mind. So what comes to mind when we're looking at this? Well, as usual, since we're doing a tree problem, chances are there's going to be some sort of traversal that's included in solving this. And so if I run with the example that they gave us, how would we deduce that? I think it was, let me get this right, 5 and 4. 5 and 4, and our output was 1, 3, 4. That was our final result. How did they do this? Well, if we're looking at the rightmost item, I think even the way of thinking about kind of the rightmost side lends itself very nicely toward a breadth first search, breadth first search. Excuse me. I'm thinking more of like a level order traversal, so kind of side by side. There could be a way to do this with DFS as well. None that obviously come to mind in my head, but the intuition when you look at this problem, I think should be to start reading these numbers somehow, these values from left to right, and you're going across level by level, and it's only that last one that you're interested in. Now, when we're doing level order traversals, typically the data structure we like to use would be a queue. The reason a queue lends itself very nicely to this is because we can add items onto a line, and we can take them off from wherever we want, especially in Python. We can grab them from either the start or the end, but I know that as I'm walking through a level, if I'm walking through this level 1 over here, the rightmost item is going to be a 1. The rightmost item in the second row is going to be 3. The rightmost item in the third row is going to be 4, right? So this value, and this value. If, for instance, I didn't have this over here, maybe I only had a 5, my level order traversal here would have to return a 5. Notice here that in this scenario, 5 is the right child of 2. 3 doesn't have any children. So somehow we need to still take into account and actually iterate through nodes like node number 2, for instance, even if it itself is not on the rightmost side of the tree. So I can't just keep walking down the right-hand side and grabbing these values. Again, for the reason that, like I said in this example, you would miss out on the 5 here. So what do? Let's think about the logic we're gonna walk through here. Imagine I'll call this QQ over here, right? Real creative. Imagine I started walking through here, and I'll add my first item to the queue, or maybe I'll initialize the queue with my root node. I think that's a pretty reasonable start. Once I initialize the queue with my right node, or with my root node, I then need to see, okay, what children do I have? So I'm going to pop this off like we do in a level order traversal. I'm going to pop this off, and then I'm going to grab the children and add the children onto the list. So I'll grab the 2 and I'll grab the 3. Now, and there's one point I kind of skipped here, which I'll add in afterwards after a couple steps. Now that we've got the 2 and the 3, what am I interested in doing? Okay. Even before I grab the 2 and the 3, excuse me, why don't I take a step back and explain what I was going to now? I've got a queue of length 1. The final item in my queue, so as I'm doing a level order traversal, the final item needs to be added to the result. I'm going to call this result. The value of this node is 1, and so I'm going to add 1 to the result. Now I can pop it off and traverse through its children. So it's got a left and a right child, so I'll add those. I'll add the 2 and the 3. Now that iteration is complete, I'm going to look at my queue and say, take the final item, whatever this last item was, and add it into the result. It is the final value, the final node of this level that I'm traversing horizontally, again from left to right. I'm going to add that on. Now, if I kind of pop it off and add it into the result, I will need to add it back into the queue because, like I said, we do need to traverse every single node here. So I'll still keep the 3 within the queue, because now what I'm going to do is as I pop these off, so I'm going to pop the 2 off and grab its children. The only child it has is a 5, so I'm going to add 5 to the queue. I'll do the same with the 3. I'll pop it off and grab its children. It's only got a 4. And now since our, and you'll see how we implement this this level order traversal. I'm not going to dive too deep into how we implement this. I have a lot of videos where I've done it, and you'll see through the implementation how we're going to go about we're just going to walk through that length of, before I added the 5 and the 4, what I'm trying to say is the queue was of length 2. When I initialize my for loop to walk through the queue, it will only go through 2 iterations because that was the length of the queue when I started the for loop. So that's why we take these 2 steps. I add the 5 and the 4. And now finally, I'm going to say again, what is the final item in my queue? The final item in my queue is this 4 right over here. It's this 4, which means it is the rightmost element of, or rather, the rightmost element of this level right here. Same thing, I'm going to pop these off and add the children. There are none. Now that the queue is gone or it's completed, we've walked through every single item, and this is the array that we're going to return. And it's all happy days from here. Since we're doing a standard level order traversal, there's no recursion involved here. It's going to be O of n time complexity, simply because of the fact that we're walking through n nodes one time each. Space complexity in a worst case scenario could also be O of n because the resultant array could be O of n. If you want to include that in your time analysis, that would particularly happen if we had a tree that looked like this, where it would have just been a linked list. So no left children, all right children going downwards. And so that's really it for the time complexities, and that's the approach that we're going to take. So again, I'm going to add items to the queue. I'm going to grab the rightmost item, the final item of the queue. That was my previous level's rightmost element. I'm going to pop it into my result. And then I'm going to rinse and repeat and grab all the children from all these nodes. And again, one final time, the reason I need to grab all the children is because if this 4 was missing, and I said to myself, okay, well, 1's got 2 children, but I'm only going to grab the rightmost child, when it gets to this level right over here, I'm going to have no insight into whether there was something left of me, left of the 3, that happened to be the rightmost element of that row. All right. So once we jump into the code, I think it will be even cleaner. But that's the general approach we're going to take. And so pulling up my code here, just again, as I like to do, I don't want to make mistakes as I'm coding through. So I got the solution in front of me that I worked on. These are the standard definitions for the class tree node. Nothing too interesting there. So what we're going to begin by doing is to actually, I was going to say initialize our queue, but we should do some error checking first. Namely, if we're not given a root, because I think they didn't tell us whether or not that's valid input. Again, that's something you could check with your interviewer. If they didn't give us a root, we could say if not root, we're just going to return either return none or return an empty array. Again, that's something you can clarify with your interviewer at the time of the asking. Now we're going to create our queue. So we'll start by initializing a queue, and we'll use the deck function, or it's part of the collections library in Python. And to it, we are going to append our root. So we're going to begin by adding that root initially so we can start the DFS. Finally, what I can do right here is create some sort of result array, and at the end, I will return that result, and this is now where we're going to do our level order traversal. Typically with these traversals, what we'll do is we'll keep looping through it while there are items in the queue. So this is kind of short form for saying while length of queue is greater than 0. So while there are any items in there, shorthand is just while queue. One thing that I said is, once we get to the top of the iteration of a BFS, I need to see what is the rightmost item of the level that I just traversed. That item would be, I'll call that last. You can call it last item or whatever you wish, really. I'm going to say a queue.pop, and I think kind of as I'm looking at this, there might be what we could potentially do is something like access the final element in the queue with a queue of -1. I'm not sure if that syntax is going to work, so I'll do it kind of a caveman way where I'm going to take it off and put it back on and then iterate through it, and maybe I can check that at the end. But either way, I'm going to take the last element and pop it off and say I want to add this element into my result array, or rather its value. So to the result array, we're going to append, again, not the actual node, but its value. So I'm going to say last.value here. And finally, again, I'm being a bit kind of simplistic here, but I'm going to add it back on. Again, I think I can refactor this at the end. I just don't want to experiment too much mid-explanation. Again, all I'm doing is I'm taking it off so I can grab its value and put it in the result, and I'm putting it back in so we can actually go ahead with the traversal. And for the traversal, we're going to do, I'm not actually going to define a variable here or give it any sort of meaningful name. I like to say for underscore in the range of the length of queue, which means just do, if there are 2 items in the queue, do 2 iterations of this for loop. I'm not going to use this variable for anything. And what we said is for the item that we're looking at, we're going to check if it has left or right children, and then we're going to add them to the queue if it does. So I'll say cur for current item will equal queue.pop left. And the reason I'm saying pop left is because when we have when we've got our queue kind of working here, imagine we had 1 was popped off, then we had a 2 and a 3. I said, let me take off the 2, and I'm going to add its children in. So add the 5 there. Then I'm going to pop out the 3. It's the leftmost item here. And then I'm going to add its children. In this case, it was only the 4. So I'm popping always the front element out, the leftmost item. I'm going to pop it out. And simply, I'm just going to say, if we have a left child, we want to append that left child to the queue. So we're going to say queue.append cur.left. Similarly, if we've got a right child, because we need to iterate through every node, we are going to say queue.append cur.right. And believe it or not, that's actually it. That's all we need to do from this code. All I'm doing is this level order traversal, popping items off and adding their children in. And this part right over here is what actually gives us that right side view. Now, before I jump in too confidently, I clearly made a mistake here. Queue is not defined. Q is not defined where? On line 6. Because I should have said Q equals, not Q dot. Sorry if you were yelling at me about that. I'm going to submit this and just make sure that it works. Cool. So for some reason that took really long. This was runtime when I ran it before with the same code, which was like, it was a lot higher performing. I don't know why that's taking so long. So I can assure you it's a perfectly efficient solution. And the one thing that I did want to look at here is I kind of popped the item off and then back on. I'm wondering if we can just say queue of -1, so the last item dot val. I think that I might just be able to do this, and that would make the code a bit easier. And actually, yeah, perfect. And for whatever reason, it went a lot quicker now. So there we go. I kind of fixed my own code midway through. So all that I did there was saying, instead of popping the item off, grabbing its value and putting it back on, I'm just going to access the end of the queue and say, this is my rightmost item for that level, add its value into the result, and do a simple level order traversal. So that's all it is for this question. Just do a level order traversal, and at every step along the way, take the rightmost item in the queue, add its value to your result, and the solution, I think, becomes deceptively easy. It kind of not undermines it. It makes the question seem easier than it was before you started. So don't be discouraged if you didn't get it right away. But I think this is a very nice solution. With that said, as always, questions, comments, feedback, drop them down below. Again, contacts in the description as always. And I will see you guys in the next video. Peace.